Okay, let's continue. In the last hour, I talked about we can use the Jacobi method. And we have certain solution procedures, and after those procedures, we can use if we try to solve the standard eigenvalue problems. Okay, that's the standard eigenvalue problems. If we use the if we follow the Jacobi's method, and we always find the off-diagonal element with the maximum absolute, and then we will post-multiply the T1, pre-multiply the T1 transpose to make the maximum absolute, to make it equal to zeros. So after several iterations, we can approach to a diagonal matrix. We can change the modified matrix into the diagonal matrix. Also remember, when we do all these transformations, the eigenvalue will not be changed. The eigenvalues will not be changed. Okay, so if we can get if the A trip prime is the if the A trip prime matrix, which is a diagonal matrix, if this matrix is a diagonal matrix, then for example if this matrix looks like this one, then we can say the for okay, so the lambda 1 is equal to A11, and the x1 is equal to 1, 0. Okay, and also the lambda 2 is equal to A22, and the x2 is equal to 0, 1. Okay, so if we can change the matrix into a diagonal matrix, then the remaining diagonal elements will be the eigenvalues. and the corresponding eigenvectors will be the column vector of the unit matrix. Okay, so if we can take out all the n column vectors, then we can get all the eigenvectors. Okay, so and also if we check the general standard eigenvalue problems, and if we can find the lambda 1, x1, that's for the first eigenpair, and also you find the lambda 2, x2. Lambda xn, and if we put all the eigenvectors into a matrix, so the n column matrix, the n column vectors in this n by n matrix. In this n by n matrix, they are the corresponding eigenvector. They are the corresponding eigenvectors. If we multiply all of these, then sometimes we call this matrix, which is the lambda, which is called the lambda matrix. And if we multiply this into this one, we have the A x1, A x2 until the A xn, until the A xn, and we know this one should be the lambda 1 x1, lambda 2 x2 until the lambda n xn. Okay. And for this one, which is called lambda 1, lambda 2, until the lambda n times which is the okay. Also, we know we can multiply the A matrix to a matrix which is formed by all the eigenvectors. Then we can get the results like this one. Okay. Okay. Also, we can check what is the lambda transpose A lambda. Okay, so in this matrix, so that's the lambda transpose times A matrix times the lambda matrix. And if we multiply this one together, it will be the we can multiply the A and the lambda matrix first. And it is also n by n matrix. The lambda transpose is also a lambda. So if we multiply these three together, okay, so we can calculate the elements of the of this one, and also we know this one should be equal to 0. This one should be equal to 0. Okay, so all the off-diagonal elements, they must be equal to 0. They must be equal to 0. Okay, so if we multiply these three together, you will get a diagonal matrix. Okay, so if we multiply these three together, we can get the diagonal matrix. Okay, and if we compare the results obtained by the Jacobi method, and if this matrix will approach to a diagonal matrix. Okay, if we make a series of the rotations, and also you can say if we make a series of the transformation of the matrix, we can approach to a diagonal matrix. Then the then if we arrange all the diagonal elements, they will be the eigenvalues. They will be the eigenvalues, and approach to the lambda matrix. So we can calculate this one. The first column vector root to x1. So so we can find not only the eigenvalues of these problems, also we can get all the eigenvectors. Also we can get all the eigenvectors. Okay. So the Jacobi's method which is the a very popular method, and also it is not very difficult to develop the program which can help you solve the eigenvalue problems. However, the original Jacobi method can be used to solve only the standard eigenvalue problems. If we try to solve the general eigenvalue problems, then we need to use the so if we have the AX lambda Emax. Okay, so for the general eigenvalue problems, the right hand side matrix we need to multiply the lambda Bx, the left hand side which is the AX, and we have not only the A matrix on the left hand side, also we have the B matrix on the right hand side. If we have a matrix like this one, also usually we will assume the A is we will assume the A matrix is a symmetric matrix. And then how can we solve a problem like this one? Again, we will try to find the T matrix. Okay, I'm sorry, I leave it here for a while. And that's the form of the T matrix. Right now I got two variables, alpha and gamma. Not like the standard Jacobi method. The standard Jacobi method, we use only one variable, theta. But for the general Jacobi method, we will use two variables, alpha and gamma. And the alpha and gamma, they are two independent variables. And that's the jth row, that's the ith row, and that's the ith column, and that's the jth column. Okay, so that's the T matrix, and the purpose of the T matrix we will like to make Aij equal to 0 and the Bij equal to 0. Okay, so now we use two variables, alpha and gamma, and the purpose of the of the T matrix we will make. So when we need to calculate the T transpose AT, and also we will make the T transpose BT. After we pre-multiply the T transpose to A and post-multiply the T matrix to the A, also we can calculate the T transpose B post-multiplied by the T matrix. After these two calculations, we like to get the both Aij equal to 0 and also the Aij equal to 0 and also the Bij equal to 0. Okay. And now I will try to derive what should be the alpha and the gamma values. Okay, so let's say the A double prime is equal to T transpose A T, and remember the T matrix, which is equal to 1 alpha gamma 1 for the I J I J. Okay, so all other diagonal elements, they are equal to 1s, and all other off diagonal elements, they are equal to 0s. And we can calculate the A prime first. Okay, for the A prime, the ith column, the new ith column will be equal to the ith column plus gamma times the jth column. Okay, so the new ith column will be the original ith column plus gamma times the jth ith column. So you can say the A prime Li, which is equal to ALI plus gamma times ALG. And also the new jth column, which is equal to the alpha times the ith column plus the jth column. So the ALJ prime is equal to the alpha times ALI plus ALG. Okay, so that's the new jth column. That's the new jth column. The new jth column will be equal to the alpha times the ith column plus the jth column. So the ALJ prime is equal to alpha ALJ plus alpha times ALI plus ALG. Okay, so that's the AT matrix. Let's say this one is A prime. This one is equal to the A prime. And after we calculate the A prime is equal to A times T, then we can calculate the T transpose. Then we can calculate the T transpose times A prime. And then the A double prime is equal to T transpose A prime is equal to T transpose times A prime. Okay. the T transpose is the they are all other off diagonal elements, they are equal to zeros, and all other diagonal elements, they are all equal to ones. And the ith row, the new ith row will be the okay, so the new ith row will be equal to the original ith row of A prime plus gamma times the jth row of A prime. Okay, so the okay, so we get the formula like this one. So we can get the formula like this one. Okay, I will take a break here, and I will continue to the next hour to try to solve the T matrix.